This call is now being recorded.
A very good morning to my lecturers, Dr. Kok Bun Siong and Dr. Ng Li Fong. My name is Muhammad Nursauzan bin Nordin from Unit Maths 2. Will be presenting my PowerPoint slide for Task 3 presentation, linear programming. My index number is 20210623100091. Before we get into the presentation, here is an overview of the content that I will be presenting. First one is the introduction. Second, applications of algebra in daily life. Model of linear programming. Solving linear programming problem with a model. And the last one is the conclusion. For the first one is the introduction. In mathematics, linear programming is a way or method of optimizing operations using constraints. In linear programming, the main objective is to maximize or minimize the numerical value. It contains linear functions which are subjected to the constraints in the form of linear equations or in the form of inequalities. Linear programming is used to find the optimum resource utilization. Therefore, it is very useful and an important technique to have. The term linear programming consists of two words which are linear and programming. The word linear refers to the relationship between multiple variables with degree 1. The word programming means the process of selecting the best solution from various alternatives. Next will be the applications of algebra in daily life. Here are some examples. The first one will be computer programming. In creating a software and applications, programmers often need to solve algebraic equations using programming languages like Java or C++. In fact, programmers are some of the people who interact with algebras more often in their daily lives. Next one is sports. In basketball, players can easily calculate the trajectories and force that needs to be applied in order to score a point from a certain distance. It is also the same with rugby and other athletic sports, where it includes estimation and movements. Mostly in sports, all of the calculation is not done directly, but it's more to naturally from the athlete own perspective. The third one will be business and finance management. Algebra is used in business to calculate profits and make more accurate decisions with the help of data and statistics. Business owners also use it to evaluate and price stocks, calculate exchange rates and interest rates. In sports, maybe we don't learn mathematics at all, but in computer programming and also in business and finance management, it is clearly that mathematics is one of the essential aspects that uh, we need to learn if we want to master in either one of these uh, work scope. The next one will be model of linear programming. There are three components in linear programming: decision variables, objective functions, and also constraints. Decision variables is in linear programming, decision variables, one of the early steps in solving problems is identifying the decision variables. It is important as it will decide the output to the solution. Usually, it is written as x1 and x2, or just like the usual x and y. Objective functions. The objective function is the real-valued function whose value is either to be minimized or maximized based on the goal of the given problem. Constraints. The constraints in linear programming are restrictions and limitations on the decision variables. There are also non-negative constraints. Each decision variables in any linear programming model must be positive. Here are some examples of decision variables, constraints, and objective function. For example, a linear programming problem, also known as LPP, about a phone manufacturing company. The decision variables can vary depending on the question. For example, X is the numbers of phone X produced, and Y numbers of phone Y produced. Or you can change the X and Y with X1 and X2. Sometimes in a linear programming problem, there can be more than two decision variables. For example, X numbers of phone X produced, Y numbers of phone Y produced, and Z numbers of phone Z produced. And same with the first one, you can change the X, Y, and Z with X1, X2, and X3, meaning that there are three decision variables in the linear programming problem. For constraints, it is usually written as an inequality. For example, 20x plus 15y more greater or equals to 50, 6x minus 3y smaller or equals to 9 for y plus 8x less than 20. Or we can change the x and y variables with x1 and x2. Just like I mentioned earlier, there are also non-negative constraints that are always positive, and it can be written just like this. X is greater or equals to 0, and same with y. As for objective functions, if I use the same linear programming problem from the decision variables, I can say that I want to determine the profit made from the production of the phone. For example, objective function equals to maximum. As for profit, it will usually be maximum to find the maximum profit from the selling of a product. So the equation for the objective function is maximize z equals to 6x plus 4y. That is an example for objective function. Now, this is solving linear programming model problem with model. This is the question about a rabbit farm. So here we can see that it also applies not just in technologic work scope, but it can also be applied in agriculture and farms and animals production. Ali owns a rabbit farm. The rabbits are raised purposely for their meat, as it has many benefits and almost equivalent to chicken and beef, maybe even better in terms of caloric and fat contents. In order for Ali to produce more quality meat, he needs to take care and feed the rabbits with the right food and right proportions. Through experience and many hours spent with taking care of the rabbits, Ali has set a certain amount of food to give to the rabbits to ensure their optimal health and thus keeping the quality of meat high. Ali needs to feed the rabbits with a daily grams of fat 32 grams of carbohydrates, and 16 grams of protein. But the rabbits should not be fed more than 4 ounces per day. As for the food, Ali usually makes his own mixture rather than buying a finished custom blended rabbit food as it is more cheaper. To make the mix, Ali will blend food X and food Y together. Food X consists of 16 grams of fat, 10 grams of carbohydrates, and 4 grams of protein per ounce. For food Y, contains 24 grams of fat, 12 grams carbohydrates, and 10 grams of protein per ounce. The price for food X and food Y are 40 cents per ounce and 60 cents per ounce respectively. So the question is, how many ounces of food X and food Y are used to make the optimal mix to get the minimum cost of producing it? To solve the problem, we need to refer to the linear programming model, just like in the earlier slide. First, we must find decision variables, then the objective function, and third is the constraints. Here, I already highlighted some of the main points. The dark blue one, ounces of food X and food Y. This will be the decision variables. X will be numbers of ounces of food X and Y numbers of ounces of food Y. You can also change the XY to X1 and X2, but I will be using X and Y in this solution. And for the purple one, the price for food X and food Y are 40 cents per ounce and 60 cents per ounce respectively. Those informations will be our objective functions, which is minimize C equals to 0.4x plus 0.6y. We use minimize because we want to find the minimum cost of producing the mix. In this table, you can see food X, Y, and the food that need to be given to the rabbits. For food X, it has 16 grams of fat, and for food Y, it has 24 grams of fat, just like in the question mentioned earlier, which I highlighted with the color green. So from this table, we can write the constraints just like this. 16x plus 24y greater or equals to 48 for the fat, 10x plus 12y greater or equals to 32 for the carbohydrates, for x plus 10y greater or equal to 16 for the protein, and there is also one line that mentioned that the rabbits should not be fed more than 4 ounces per day. So with that, you can write that x and y lesser or equals to 4 because x and y refers x and y is the weight for food x and food y. And lastly is the non-negative constraints, which are just like this, greater or equals to 0 for both of them. Now, from the constraints, we can calculate the coordinates that we will use in the graph in the next solution. So for the first one, which is the fat, I will divide all of them with 48 so that I can have an equation that is greater or equals to 1. So the x and y will be x over 3 plus y over 2. From this equation, we can see x is equals to 3 and y equals to 2. That will be our coordinate that we can point in our graph later on. Same with the carbohydrates. I will divide all of them with 32 so I can have greater or equals to 1, and I will get x equals to 32, y equals to 27. Same as this one also for the protein. Divided by 16, I will get x equals to 4, y equals to 1.6. And for the weight, x plus y less or greater than 4, less or equals to 4, I will divide them with 4. So I will get x over 4 plus y over 4. And x equals to 4 and y also equals to 4. With all of the coordinates that we have got, we can finally plot it in the graph. So this is the graph. As you may see, there are two more actually inequalities that we didn't show, which is the x greater or equals to 0 and y greater or equals to 0, because the graph, it will just be in the same line as the x-axis and also the y-axis. So we can plot it and make the graph. For the blue one, it is for the carbohydrates, and the green one, it is for the fat. For the lime colored line, it will be the protein, and the purple one will be the weight. So this region is called feasible region. So how do we actually get the feasible region? So as you can see, we can start from the lowest line in the graph. I can choose this green one. It is actually positive because it is greater or equals to 1. So as we know, if it is positive, then we can shade the region up or to the right of the line. So we can shade this region, and it is the same with the lime colored line. Shade the up or to the right of the line, and same with the blue colored one. But for the equation for the weight, it is negative because it is less or equals to 1. So we will shade the region going to the left or down of the line. So if we can see all of the shaded region from 4 of these lines, we can detect a region where all of the shaded part kind of intersect with each other, where in that part there will be all of the shaded region on top of each other, and that is the feasible region right here. And I have already shaded it, so it looks like this. Now that the graph is done, we can find the optimum point. By finding the optimum point, we can substitute the value of x and y into the objective function to find the minimum production cost of the mix. So we can use a guideline or reference line. And how do you use a reference line is using the objective function. We can let c equals to 0.8 from the objective function earlier. So 0.8 equals to 0.4x plus 0.6y. Basically, I just divided all of these with 0.8, and I will get x over 2 plus 3y over 4 equals to 1. So the coordinate will be x2 and y 0.75. And this, the lowest line will be the reference line and guideline. So with the reference line, firstly, before we use the reference line, we must mark all of the corners on the feasible region, just like this, A, B, C, and D. And from there, we can use the guideline or reference line and go up until it touches the first point from 4 of the corners. And in this situation, as we can see, the reference line touches point D first. So we can say that point D is the optimum point. And you can prove that by doing this, by taking all of the points A, B, C, and D and substitute it into the objective function C equals to 0.4x plus 0.6y. And we will get this. For A, we will get 22 ringgits and 40 cents with food y only, because as you can see, for x it is 0, so x will be 0. And for point B, it is 1 ringgit 62 cents, cheaper, a little bit lower than point A, also using food y only. And C, 1 ringgit and 90 cents, and D, which is the optimum point earlier, 1 ringgit and 60 cents. As we can see here, D has the lowest price among the others, the 4 points that have been given in the graph. So we can see that it is the minimum production cost, which is the cheapest one. Then D is the right answer, proving that the guideline, the reference line, is correct. So the final answer will be the minimum cost is 1 ringgit and 60 cents per daily serving, using only 4 ounces of food X only. Conclusion: linear programming is an essential topic to learn in mathematics because it serves many benefits and it is important in our daily life. The example shown is just a glimpse on what linear programming can do, when in reality, many scopes of work and daily activities can sometimes rely so much on it to solve problems. Without it, I do not think that we can achieve the many things that we enjoy now, such as technology, economic balance, and also high-quality products. So we must be grateful for the people before us, most specifically George B. Dantzig, who is the creator of linear programming, for giving one of the most powerful tools of math, not just to be used in mathematics, but also in our daily life. That is all from me. Thank you.